remember one of the classes I mentioned this coffee cup example, where I just place a coffee cup here, and then which is let's say at 50 degrees, 60 degree, whatever temperature, and then you leave it out, leave it there isolated. Slowly it's going to reach equilibrium with the surrounding temperature, let's say 25 degrees. Okay. So now one would guess that obviously there is conduction mode of heat transport, but what is not obvious to see is that there is also convective mode of heat transport in the same process. So note that in this example there is no pressure driven flow, it's just fluid which is sitting in a coffee cup, right. So what happens is that the density differences that will result because of change in the local temperature is going to lead to what is called free convection flows. Okay. Now an easy way to see that is, suppose I have a box, okay, which is filled with a fluid, very similar to your coffee cup example, except that I now close the top, okay, and I will make sure that the fluid is filled all the way to the top of the enclosure. So now if I maintain, let's say that I maintain the temperature of the top surface as T1 and the bottom surface as T2. Okay. Now if T1 is greater than T2, okay, what can we say about the densities? Density is a function of temperature, right. So what can we say about the density? Temperature is higher, density will be lower, right, because when the temperature is higher, you allow the fluid to expand, and so we expect that the density of the fluid at the top surface is going to be lower than the density of the fluid at the bottom surface. So that's a very stable situation, where light fluid is now sitting on top of the heavy fluid. So that's a very stable situation. Now if I take a parallel where I put T1 is less than T2, so let's say I am able to maintain the temperature above which is lower than that of the temperature below, and in fact this is what happens when you leave the coffee cup idle on a table. So the bottom of the table temperature would quickly equilibrate with that of the coffee, and the top is now exposed to the atmosphere which is at a lower temperature. So you expect that the density of the fluid near the top surface is going to be greater than the density of the fluid in the bottom surface. So that's an unstable situation where you have a heavy fluid which is now sitting on top of the light fluid. So what will gravity do? It will immediately pull the heavy fluid to flow below, and the light fluid will move on. So gravity will act on it now. Gravity will act on it and it will pull the heavy fluid down, and so what it results is a circulation of the fluid. Okay. So this results in a recirculation. So this results in a recirculation of the fluid, although it's in the same enclosure. You are not adding extra fluid from outside. There is no forced convection. The fluid is not forced to move. There is no pressure driven flow. It's simply because of the temperature difference. It results in the density difference, and so gravity will now start playing a role, and there will be recirculation of the fluid. Okay. The moment there is recirculation, you start having convection currents. Right. So whenever there is flow, you have convective mode of heat transport. Okay. So what we are going to see is how to characterize the convective mode when you have free convection, what we are going to see is characterize heat transport in natural convection. Okay, so that's what we're going to see. So the first example we're going to look at is, suppose if we have a plate, let's say a vertical plate, okay, which is, let's say, maintained at a temperature Ts, and there's a lot of fluid which is present, and suddenly I am putting this vertical plate into the fluid. So there's a fluid which is now stationary, it's not moving, but I'm suddenly putting this into the fluid. Now this is not a bad example. A lot of quenching process industries actually done this way, where a hot material is suddenly dumped into water. Okay, so suppose I have quiescent fluid. I have quiescent fluid which is sitting around. Okay, quiescent means it's basically stationary or sitting idle. This fluid which is just sitting idle, it's not moving, not doing anything. Okay, and therefore the bulk velocity is 0 in all directions. So if I give coordinates now, if this is my x direction and if u is my x component velocity and this is y direction, v is my y component velocity, then both u and v are 0 in bulk. Okay, but then what happens to the fluid which is close to the plate? Because the fluid, so let's say that this is a temperature T infinity, which is smaller than the temperature of the plate. That's exactly what you do when you have a quenching exercise, where you want to reduce the temperature of the material, and so you quickly dump it into water. Okay. So now, if supposing the bulk temperature is smaller than that of the plate temperature, then very close to this plate, the fluid which is present is now going to have a density gradient. Okay. And that leads to what's called a boundary layer. And explain in a minute why this boundary layer is formed. Okay. So suppose I look at the fluid particles which is very close to the surface. Okay. So they will quickly equilibrate and they will reach suppose this is the layer very close to, next to the plate. Okay, that's a layer next to the plate. So they will quickly attempt to equilibrate and reach the temperature of the surface. Okay, so which means that, so supposing if the density of the fluid in bulk is rho infinity, then what will be the density of the fluid here? It will be greater or lesser? It will be lesser, because we said Ts, the surface temperature, is larger than the fluid temperature, right? So if I call it rho 1, this will be lesser than the bulk density. Okay. So now if I look at, so supposing I go further down into the plate, now the fluid which is present in this location is exposed to the surface of the plate for a much larger period than the fluid which is present here, right? So I am just dumping it inside. So these fluid particles which is present at this location will now have a density gradient. So supposing I say that rho 1, okay, so now it will have a density gradient. Okay. It will slowly reach the density of the bulk. Okay. So this density of the fluid here, this is the density profile. Density of the fluid here will be lesser than the density of the fluid in the bulk region. Okay. So therefore, close to the surface, you establish a density gradient in the vertical direction. And so the fluid which is present here, so this is a bulk fluid, so the bulk fluid will start flowing down, okay, the fluid which is present close to the boundary layer, okay, will start flowing down, and the fluid which is present here will start moving up. So this sets up a recirculation, and this leads to a conductive mode of heat transport very close to the surface, not far from the surface. And these boundary layer thickness is typically much smaller than the boundary layer thickness that you would get in a forced convection system. So therefore, what we are going to see how to write these equations for this kind of a problem and how to find heat transport coefficient for this kind of a problem. So supposing I take a density profile here, okay. Now I look at the density profile in this location here, okay. Now I look at any plane here, any plane at any y, let's say y1, okay. So this density profile is going to cause a density gradient in y direction, and therefore it's going to move down. It's going to move up here. So one thing, yeah, why should what? Right. Correct. No, see, when I say it is rho 1, it will try to quickly equilibrate. But then, as soon as you drop the plate inside, okay, not every location is going to equilibrate immediately, okay. So as soon as you drop the plate itself, you will start seeing recirculation of the fluid. But this aspect of it reaching the same temperature and the same density is after the plate is exposed to a sufficient time inside the fluid. So the recirculation will start as soon as you drop the plate inside, okay. So that's a transient. So the transient itself will set off the motion for convection in the boundary layer, and that will continue as soon as the plate is still placed inside, after the plate is placed inside. Y direction, yeah, this is gravity is in this direction. Correct. Right. Yeah, but you have to be very careful that here the motion is going to be two-dimensional. Okay, I gave a one-dimensional example just to get an insight, but really the motion is going to be two-dimensional. Okay, so even though the gravity is acting in section below, there will always be a component which will actually make the fluid to move on the other side. So it's a two-dimensional motion. You will have both u and v inside the boundary layer. Rho at where? Yeah. Yeah, that's correct. Right, but that is if you are looking at only one plane, but the boundary layer is not a plane. Boundary layer is not a single plane, right? So if the boundary layer, supposing if the boundary layer were also to be a single plane, then you would expect that nothing is going to move. But the extent to which the fluid is feeling the presence of the plate is not the same at every location along the plate. If it were to be same at every location along the plate, then what you say is right. But it's not the same. So therefore, you are going to set up a two-dimensional motion. And that's the reason why you have a certain shape. Okay. So anyway, so what we are going to see now is how to characterize this equation. So far, we always ignored the effect of gravity, and in fact, we ignored the effect of what is called the body forces. So what we are going to see in today's and the next lecture is how to include the body forces and characterize the heat transport process. So we have to write the momentum balance. So in order to characterize these processes, we need to write the corresponding balances. So let's write the x momentum balance. Okay. So what's the x momentum balance? So let's say what are the processes which are involved. So remember, there are two ways of writing it. You can start from first principles, from shell balances, or you can identify what are the different processes, and you know what is the mathematical representation of each of these processes, and you put the correct sign and join them. So what are the processes? So you have convection. You have convection in both x and y direction, x direction and y direction. You have conduction process, then you have pressure gradient, and then you have body force. So these are the 4 terms which are involved, and so we can easily write the X momentum balance. U du by dx plus V du by dy, that is equal to minus 1 by rho dp by dx minus g plus mu into d square u by dy square. Okay. Now this is after assuming boundary layer approximation. Okay. I am including the boundary layer approximation. So this is the x momentum balance, and the y momentum balance will simply be dp by dy, that's 0. So that will be the y momentum balance when you introduce the boundary layer approximation. Okay. So what we will do in the next lecture is how to take this momentum balance and the energy balance that we are going to write, how to non-dimensionalize it. Remember that when we non-dimensionalize for all the cases we did so far, there was always a reference temperature and reference velocity. We always had a free stream velocity and free stream temperature. Unfortunately, there is no free stream velocity here. We have a free stream temperature which is T infinity, but there is no free stream velocity. So we are going to now see in the next lecture as to how to handle this kind of a situation where there is really no reference velocity, still how to non-dimensionalize it and to characterize the processes and what kind of non-dimensional quantities that we will get.